Hey everyone, welcome to Module 8. In this module, we'll be taking a look at confidence intervals, which are a cornerstone of inferential statistics. And inferential statistics is a cornerstone of research. So there is a ton of value and application to what you're about to learn. My goal in this first video is to look at confidence intervals for population means. And ultimately, we want to be able to estimate the true mean of a population by just working with a single sample. So here's the example that we're going to use. An IQ test was given to a simple random sample of 75 students at a certain college. The sample mean IQ score, 105.2. Scores on this IQ test are known to have a population standard deviation of 10, and our task is to estimate the population mean of IQ scores for college students just based upon the results of a single sample. So at first glance, the best choice that we have for estimating the true population mean would simply be our sample mean of 105.2, and we would call that a point estimate. But a point estimate might not be the best way to estimate a true population mean, because as we've recently seen, when we take a sample mean, we don't know where it is in the distribution of sample means. So here's my X-bar distribution, the distribution of sample means. Remember, the middle of that is the true population mean, and this is what we're actually trying to estimate now. But we don't know if 105.2 is near this true population mean, or if 105.2 is maybe somewhere over here, or maybe it's even in the lower tail or even the upper tail. We have no idea where, we have no clue where 105.2 is in the distribution of sample means. And so this is our problem. And our way around this problem is to quite literally provide a margin of error on either side of 105.2 and create what we call a confidence interval. And so a confidence interval is going to be starting with a point estimate and then adding and subtracting a margin of error to that point estimate. Now, we don't know where 105.2 is in this distribution of sample means, but just to illustrate this concept of the confidence interval, let's pretend for a second that 105.2 is somewhere right around here. And if 105.2 is right there, you can imagine that it's not the worst point estimate for the true population mean, but it's also not the best. And hopefully you can also see that if you went a certain margin of error on each side of that point estimate of 105.2 and you created an interval, then the interval would have a really good chance of including that true population mean. And that's the whole idea behind these confidence intervals. We're trying to create intervals where we will have a lot of confidence that the true population mean is going to be inside that interval. So really the next big question is, well, how wide do you make the interval? How do you ensure that certain level of confidence that the true population mean is going to be inside that interval? And it really all boils down to the empirical rule. So let's go talk about the empirical rule for a little bit. And so I've got another distribution I want you guys to look at here. And this is just the same sample mean distribution. But recall the empirical rule was the 68, 95, 99.7 rule. And that rule was 68% of your data was within one standard deviation of the mean in a normal distribution. 95% of your data was within 2. And almost all of your data in a normal distribution was within 3 standard deviations of the mean. So we're going to focus on 95% of the data in a normal distribution being within 2 standard deviations of the mean. And to be a little bit more accurate, it's not precisely 2, it's actually 1.96. So in the context of a distribution of sample means, I can state that 95% of sample means are within 1.96 standard deviations of the true population mean mu. Or based upon this picture, if you start at mu in the middle and you deviate 1.96 standard deviations on either side, we know that we have 95% of our data in there. 95% of our sample means are in that range. So let's take a look at a few of those sample means. This could be one right here. This could be one right here. This could be one right here. So if you took a look at this sample mean right here, can you see that this particular sample mean is less than 1.96 standard deviations from the true population mean mu? Can you see that this sample mean right here is less than 1.96 standard deviations from the true population mean mu? And same thing with this one. But as soon as you get outside these red lines here, then those sample means would not be within 1.96 standard deviations of the true population mean mu. Okay? Now I can take this statement and I can state it another way that's actually going to be very meaningful for us when it comes to confidence intervals. And that is, I can state it like this. I could say, instead of this, I could say 95% of the time, the true population mean mu is less than 1.96 standard deviations from the sample mean. And so if you again look at this sample mean, you start at the sample mean, can you see that in this case, the true population mean mu is less than 1.96 standard deviations from my sample mean if it was right here? Or can you see if my sample mean is right here that the true population mean mu is less than 1.96 standard deviations from this? Same thing right here. If 1.96 standard deviations is this yellow distance, then mu is less than 1.96 standard deviations from that sample mean. And in fact, 95% of the time in a distribution of sample means, the true population mean is less than 1.96 standard deviations from the sample mean. Now what I want to do is I want to take this statement and I want to break it down a little bit more in terms of confidence intervals. And so let's look at these following graphs now. So I basically want you to see a few different possibilities of where the sample mean could be, and then I'm going to generate confidence intervals from those sample means. And in the process, I hope that you'll see that this statement is going to make sense. Okay, so in this first picture, you can see that I've got my x-bar distribution, and I'm pretending that 105.2 is right here, and I am deviating, as this statement says above, 1.96 standard deviations from the sample mean. And so if my sample mean was right here and I went 1.96 standard deviations on this side, 1.96 standard deviations of this distribution of sample means on this side, you could see that I do create an interval that is going to contain my true population mean. Here's another sample mean, or another possible location for our sample mean of 105.2. Again, if you deviate 1.96 standard deviations on this side and 1.96 standard deviations on this side, again, you create an interval that contains that true population mean. And I want you to see, or I hope that you see, that anytime the sample mean is going to be between these red lines, when you deviate 1.96 standard deviations from that sample mean, that it is going to create an interval that will in fact include that true population mean. However, if you get something like this, where you have a sample mean, and maybe our sample mean of 105.2 is outside that red cutoff area, it's the same red cutoff area from up here, you can imagine that if you deviated 1.96 standard deviations on both sides, that you would create an interval that would not be covering the true population mean. So based upon these few pictures that you see right here, we can theoretically consider that 95% of the time, the true population mean is going to be contained in the confidence interval created by deviating 1.96 standard deviations on either side of the sample mean, in this case of 105.2. This is really important because we don't know, when we take a sample mean, where our sample mean is. When we had 105.2 as our sample mean IQ, we don't know if 105.2 is here, or if it's outside those extremes. And therefore, we don't know where our confidence interval is either. And so we can go through this process of creating a single confidence interval. However, we don't know if the confidence interval that we create is going to be this one, or if it's going to be this one, or if it's going to be this one. So we have to rely on the fact that 95% of the time when you would go through this confidence interval creation process, you'll end up with an interval that will contain that true population mean. And since 95% of the time that you go through the confidence interval creation process, you would end up with an interval that would contain that true population mean, that is why we call it a 95% confidence interval. Okay, so let's take a look at what this means algebraically and how do we actually compute what these confidence intervals are. Well, algebraically, deviating 1.96 standard deviations on either side of the sample mean looks like this. You start with your sample mean, your x bar, you add or subtract 1.96 standard deviations of the distribution of sample means, which remember is sigma divided by root of n. And so in our example, our x bar was 105.2. We're adding and subtracting 1.96 standard deviations on either side of that. Remember, our sigma in the problem was 10, and our sample size was n equals 75. I don't have the calculator pulled up right here right now, but if you just put into your calculator 105.2 minus 1.96 times 10 divided by the root of 75, you are going to get a lower bound of 102.94. And then if you did 105.2 plus 1.96 times 10 divided by root of 75, your upper bound for the interval is going to be 107.46. And so we can state with 95% confidence that the true population mean IQ of all college students is in this interval. Now remember, we don't know where that interval is. We don't know where our sample mean is in the distribution of sample means. So we're not sure if 102.94 up to 107.46, if it's something like this one, or if it's something like this one, or if it's something like this one. But we can be assured, based upon the process that we're going through, that we should have 95% confidence that this interval does in fact contain that true population mean. Okay? Now, on the positive side, you don't really have to worry about calculating this by hand. You're never going to be doing this in this class. We're going to be using calculator tools that will be handling all of this algebra. But I still think that this theory that you're seeing here is going to be very helpful for you, especially as we start to look at some examples where we have different confidence levels other than 95% confidence levels like you're seeing in this example. In some later videos, you're going to see we can have 90% confidence levels or 99% confidence levels, and a lot of what's going to change when you adjust the confidence level is simply the number that you have right here. Instead of the 1.96, you might have a different number, and again, all of that kind of goes back to the empirical rule. So that's where I'm hoping that this theory is going to help you a little bit as you're thinking about this. Now, in the next video, I'm going to walk you through a simulation where we know all about a population, and we'll observe how the sampling process can sometimes result in sample means that are in the extremes of the sample mean normal distribution, and therefore you could see how confidence intervals could be created that would not include or not cover that true population mean. Now that should happen a small percentage of times as we're looking at confidence intervals that are 90, 95%, 99%, things like that. That suggests that we're going to have a high level of confidence that our intervals are going to be including that true population mean, but there will always be a small percentage of times where that true population mean will not be inside that interval. And the tough thing as a statistician is you never really know when you have a single set of data and you collect a single sample mean and you get that single confidence level, you're really not sure if it is that confidence level that contains that true population mean or not. But the confidence is on our side. Okay, so check out that next video and you can observe this theory a little bit more before you get into some examples and calculator tools in some of the later videos. Thanks for checking this out.